So we've been looking at average rate of change, instantaneous rate of change, looking at limits as h approaches 0 to get that instantaneous rate of change at some x value. And so here on your screen, you should be seeing this graph. Maybe this is f of x. And we actually have multiple secant lines. So secant lines were the lines that joined 2 points on a function f of x. And notice as this h value, again, is going closer and closer to 0, of this function f of x, and this is maybe x equals a. We saw that this was f of a plus h minus f of a all over h. And that gave us a couple different ways that we could write this. The instantaneous rate of change at x equals a. We also could say this is, we can also say that this is the slope of the tangent line at x equals a. So if we looked at this, the one piece that is giving us the exact slope when x equals a looks like this. And so they're all increasing, so we have some sort of an idea. This one was the tangent line. All giving us kind of an idea of what the slope is at x equals a, but as h goes to 0, we got points closer and closer to x equals a. That was giving us the instantaneous rate of change, or another way to say it, the slope of the tangent line. Okay, so we already wrote this out, the derivative of a function f of x at a number a. We gave you new notation, this f prime of a, and that reads f prime of a. Or another way to say that, the derivative of f at x equals a. So if you see that notation, that's how we would say it. So we've been working with the definition, the limit as h goes to 0 of f of a plus h minus f of a over h. But there's another definition that will give us the same thing. We can look at it as a limit as x approaches a of f of x minus f of a all over x minus a. Okay, so again, I just kind of mentioned it, but there's different interpretations, meaning the same thing, the slope of the tangent line at x equals a, the instantaneous rate of change at x equals a, and I didn't bring this up, but also if we were looking at the position function and we wanted to find the velocity at x equals a, the speed at x equals a, and this is also another interpretation of the derivative of x at x equals a. So another way to say this, we say a function is differentiable at a if f prime of a exists. Okay, so the derivative exists at x equals a. Another way to say that is it's differentiable at x equals a. It is differentiable on an open interval a, b, if it is differentiable at every point in the interval. So if f is differentiable, one thing that we can say then, f has to be continuous at x equals a. I'm going to come back with that with another in a minute. But note that this does not go in the other direction. So this does not hold. Not necessarily hold. If f is continuous at x equals a, then it also is differentiable at x equals a. This does not necessarily. The other direction. If x is continuous at a, it is not necessarily I don't even know if I'm spelling that right. Necessarily, I'm not. Differentiable at a. And we'll see an example of that a little bit later when we look at an example of the absolute value of x and seeing if it's, we know it's continuous at x equals 0, but we'll show that the derivative actually doesn't exist there. Okay, so the following conditions have to hold in order for a function to have a derivative at a particular value. So first of all, f has to be continuous. So this is kind of a good review of last chapter. So a function is continuous. Remember, 3 things had to hold. So one of the things that had to hold was that the function had to exist at that value. So f of a exists. Another way to say that is a is in our domain. The other thing that had to hold was a limit exists. So the limit as x approaches a of our function f of x has to exist. So recall, for a limit to exist, a couple things had to hold. That the limit as x approaches a on the left-hand side of f of x, remember, had to be the same value as if we were approaching it on the right-hand side of x equals a. And it was going towards one y value. It wasn't shooting off to infinity or negative infinity. And then the last condition that has to hold, and I think I'm running out of room, so hold on. Last thing that has to hold is that the limit as x approaches a of f of x, that value that we got has to be the same as if we were plugging in a wherever we saw an x, f of a. So we know, again, it's continuous at a value x equals a if all 3 of these conditions have to hold. All have to hold. So we know if it's continuous, then the derivative may exist, not necessarily will exist. The function has to be smooth. And so recall, to be smooth, there was no jagged corners or jagged points. Another way to say that, sharp corners. And we have to say that it does not have a vertical tangent line. So vertical tangent lines, there's a couple ways that this can happen. It could be continuous, but might become a vertical tangent line for a little bit and go on. And so in this case here, the derivative would not exist. The other condition where you would have a vertical, could have a vertical tangent line is if you have our vertical asymptotes. Right, so if we came up like this, notice as x is approaching a, these values over here, that tangent line is vertical. Okay, so the derivative does not exist where all the following conditions are true for function a. So basically the same thing we were kind of saying up here. It had to be continuous, so it can't be discontinuous. So we don't have no jumps in there. Or asymptotes, vertical asymptotes. No holes in the graph. So those would be values where it was discontinuous. You can't have a sharp corner. So if we had something like this, at this value where it has this sharp corner, the derivative does not exist. It's continuous there, but the derivative does not exist. Again, it has no tangent lines, vertical tangent lines. Remember, vertical tangent lines was where you have 0 in the denominator, but not also in the numerator. And those were values where the function's undefined. So we already showed you what that could look like from above. And for this class, we have one other case. Looks like it's. So the other area that you have to worry about is wild oscillations. And so we had seen that happen where we had y equals sine of 1 over x. Remember, as x was approaching 0, we came up here and it started to go back and forth really, really fast. And so in this case, there would be it would not have a derivative where that's happening. Okay, so given a graph, you should be able to look at it and you should be able to tell where the derivative exists and where it doesn't exist. So looking at the following graph, determine the x values where the derivative does not exist. So I'm going to let you think about that for a minute and then we'll come back and talk about it. Pause the recording. Okay, so you should have found the following values where it does not exist. So let's move from the graph from left to right. And so coming over here, I noticed that we have a sharp corner here. And so -1, -2, -3. So x equals -3. So yeah, discontinuous, or no. Derivative does not exist. At x equals -3, because we have a sharp corner. It doesn't exist where we have jumps in the graph. So notice there's a jump in the graph. So at x equals -2, there's a jump in the graph. At x equals 0, notice you have a vertical asymptote here. And it's undefined. So x equals 0, there's a vertical asymptote. And then one other case, notice that this is an open circle. And so that would be at x equals 3. There's a hole in the graph. If you kind of think about, again, what the derivative means, it's telling us the rate of change at one particular value on our graph. And so the reason why these sharp corners don't have a derivative, it really depends on which way we're coming in. If you are looking at this value here at x equals -3, and we looked at the slope, remember it's the slope, and then we're getting closer and closer to x equals 3 on the left-hand side, I'm going to have a different slope here than if I was approaching x equals 3, -3 on the right-hand side. And so I'm not getting the same slope at this sharp corner, and that's why the derivative at that value doesn't exist. Well, you're not going to have any rate of change if that value x equals a isn't defined. And so these open circles are where, or asymptotes, vertical asymptotes, not horizontal, or these jumps in the graph are values where, well, actually jumps in the graph, it could be defined, but these vertical asymptotes are the whole, it's not defined. So jumps in the graph, yes, your function could be defined at that value, in this case of -2. But again, it depends on, are we coming in the left-hand side or the right-hand side while we're looking at that limit getting closer and closer to that x value. If I'm getting closer and closer to this x equals -2 on the left-hand side, this would show that my rate of change in this case is increasing. Where if I was looking at points as x getting closer and closer to -2 on the right-hand side, and I would look at this and find the slope at that particular value, it would be decreasing there. And again, I'm not having the same slope, and so it doesn't exist, the derivative. Okay, so let's look at an example where we're trying to find the derivative of f of x equals the absolute value of x at x equals 0. Okay, so recall, if we're looking at our function, f of x equals x, absolute value of x, it's really a piecewise function because it depends on what value we're plugging in for x and what value we're going to get back. And so basically, we're going to use the absolute value of x. We're going to use the same number we plug in if x is greater than or equal to 0. Right? So if I plug in 0, my y value I get back is also going to be 0. It tells me to use this equation. If I plug in 2, absolute value of 2 is the same number, 2. If I plug in a negative number, though, in order to do this, so if I plug in -1, When I take the absolute value of -1, I'm taking the opposite sign. I'm taking the negative of -1, which gives me +1. So if x is less than 0, we're using this equation. We look at the graph here. And if you graph this function, recall this is like a V shape and we have a short corner. Let's go and look at this using the derivative. Formal definition. So we're looking at the limit as h is approaching 0. This is our f of x function. So we're going to plug in and our a value in our case, a equals 0. So when we plug in f of a plus h into this function, wherever we see an x, we have the absolute value of 0 plus h minus f of x function, which is just the absolute value, and a, so f 0, all over h. And so if we look at this, we get the limit as h approaches 0. This is equal to the absolute value of h all over h. Okay, so this again doesn't tell me anything. If I plug in 0 in here, I would get 0 over 0. And that's an indeterminate form, and that's where we would have to go back and manipulate it. So let's look at the limit as h is approaching 0 on the left-hand side. If I was doing that, then when I'm plugging in a negative number in here, the result is positive, right? Absolute value of a negative is positive. So this is the same thing as h over, now plugging in a negative number here. So this is h over negative h. And this is equal to -1. Where if we look at the limit as h is approaching 0 on the right-hand side, well, if I'm approaching 0 on the right-hand side, then I'm plugging in positive numbers. So the absolute value of a positive number is just h itself, all over. Well, if I plug in a positive number in here for h, I get back positive h, because it was a positive number I was plugging in, and this is equal to 1. And so my derivative coming in on the left, the slope here is -1. And the slope as we're coming in here on the right-hand side, the slope is 1. Our slopes are not the same at this sharp corner. And so the limit does not exist. So recall part of our definition when we're looking at the limit as x approaches a, the derivative of prime of a, it had to occur that the limit exists. This limit doesn't exist, so it's not differentiable. So this is not differentiable. At x equals 0. So we've already kind of done this where we were looking at the derivative of our function f of x, and then we went in and we plugged in values where we're trying to find the derivative. This is our next section, so I'm kind of tying in that. I was tying in that next section we were going to do. So here's the definition of the derivative, where we can find the derivative anywhere on a function if it exists. So it says the derivative of f of x with respect to x is a function, f prime of x, like we said, that's how we would read this, and is defined as follows. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So before, the only difference was that we had a number for x, and that's what we were plugging in. Okay, so there's a lot of different notations of how to represent the derivative. Let's see. Sorry. So the typical notation is what I have been showing you, the prime notation. However, there's other notation that is occasionally used, so we need to cover that. And your book will go through using all the different notations. So you have to just be familiar with the different notation and just, this is meaning the same exact thing. So given a function f of x, all the following are equivalent and represent the derivative of f of x with respect to x. So we might have a function that doesn't have the variable x. We might have our function in terms of time. And so this is just saying our variable in this case is in terms of x. So f prime of x, we can write it as, remember f of x is just the same thing as writing y is y. So we can write that as y prime. Other notation is df all over dx. And so this reads, in this case, it means the derivative of f with respect to x, but it reads df, say the letters, and then dx. Well, if I was defining my function in terms of y instead of function notation, that's the same thing. I could write it as dy over dx. And I would say dy dx equals, another way to say this, d dx of our function f of x out here. So d dx of f of x means the derivative with respect to x of our function f of x, and then another way, d dx of y. So those are all the derivative of a function anywhere where the derivative exists for some value, x equals a. But if we wanted to figure out what the derivative was at one particular value at x equals a, there's another couple ways that we could also write that. And we were seeing that from yesterday. So we could write this as, I'm sorry, I'm going to just blow it up again. F prime of a. Another way to write f prime of a, so we're taking the derivative, we're evaluating it when x is a. We can write this as y prime with a vertical bar, and then on the bottom, you're telling what you're evaluating it at, so x equals a. We can write it as df dx, and then with a vertical bar, x equals a, or dy dx with a vertical bar, x equals a. And sometimes now when we're dealing with function notation, we actually don't put that x in there anymore. We could just call it f. So function f. So f prime of x, if you see it as just f prime, they're meaning the same things. So we have a theorem that says if, and I already stated this above, says if f of x is differentiable at x equals a, so the derivative exists at x equals a, then we can say that it has to be continuous at x equals a. So if we find a derivative exists there, then we know that it's continuous there. Again, the other way doesn't go necessarily hold. If we find it's continuous at x equals a, it might not necessarily have the derivative there. And we saw that with the absolute value function. It's continuous everywhere, but it's not differentiable at x equals 0. Okay, I think that might be all I put in my notes so far. So let's pull up some examples and go over these. Just start a new video with examples. Before I do that, let me just pause it and see if you guys have any questions.